Greetings developers. So it's been a while since I did my last video, but I thought now in those COVID-19 times it might be a good idea actually to do another one. And so I'd like to again go through some test-driven development exercises and also do the exercise on the Mars Rover Kata. Because the Mars Rover Kata is actually a good kata. So if we look at the rules, I have them here in the web. So if we look over the rules, there's quite a bit of freedom how this rover can be designed, and I'd like to go through today I'd like also to introduce a library I have written a couple of weeks ago for Common Lisp. It's called cl-gserver, which is basically an implementation of the Erlang gen server, which is basically an actor, right? So if you want to know how the roots about actor-driven development or actors, the actors pattern, then you need to look at Erlang, because they had the first, and the whole Erlang virtual machine is dealing with this stuff. So we want to implement the Mars Rover as an actor, and when we go through the rules, we will see that there's a little bit of there are different options how to design this rover, and yeah, I'd like to go through this. So I don't want to implement this complete until the end, until the rover is complete, or until all those requirements are complete. I just want to give an idea, or yeah, I don't know. So I just want to carve out the concepts of, or the concept of how this rover implementation can work with using actors. So I don't want to take this very much longer than an hour or so. Yeah. Yeah, and I don't need a fancy test set. Don't need a fancy project setup. We just use Sly in Emacs, and we just use the REPL and two text files. So, but let me just read through the Mars Rover Kata text so that we all understand what it is about. So your task. You're part of a team that explores Mars by sending remotely controlled vehicles to the surface of the planet. Develop an API that translates the commands sent from Earth into instructions that are understood by the rover. Requirements. You are given the initial starting point XY of a rover and the direction north, south, east, west it is facing. The rover receives a character array of commands. Implement commands that move the rover forward, backward. Implement commands that turn the rover left, right. Implement wrapping from one edge of the grid to another. Planets are spheres after all. Implement obstacle detection before each move to a new square. If a given sequence of commands encounters an obstacle, the rover moves up to the last possible point, aborts the sequence, and reports the obstacle. So, let me first fire up Sly. And let me create a new buffer for a test, because that's how we work, right? So we create a test first. So when we read through those rules, there are a number of design options. So when I read this reports here, it kind of, so reports is kind of an action the rover does, right? So it's not like someone in the outside world would query for this report, but the rover actively notifies someone of this obstacle, and actually I want the rest to work in a similar way. So I could imagine that there is some kind of a reporting facility the rover reports to, or reports its state, state changes, or not state changes, a new state, and also those obstacles. So yeah, so when we say we want to implement the rover using as an actor, there could be another actor which the rover knows about, right? And the rover sends state information to this reporting facility, and in the test we can then test against this reporting facility or the state this reporting facility has. So we're doing here a little bit. So when we think about test-driven development, there are two styles of test-driven development. So the classicist is what Kent Beck came up with more than 20 years ago. The classicist is this red-green refactor cycle where you are in this workflow. You have a failing test, you make this test pass as quickly as possible, and then in the refactor phase, where you remove the faking, and so you try to implement the real thing, and you also carve out design in this refactoring phase, right? So you make refactorings, move components or create components, and you need to think about, is this component is this component a composition, or is this an aggregation? And the other style is outside in. So in outside in, the designing is more done in the red phase. So you think more, you do a little bit more planning in the red phase, where you actually think about those things beforehand, before you write the test, right? So you would think about so this obstacle detection, or is there a navigational component of this rover that is maybe autark, right? So can this live for itself? Then you have an aggregation, and this component needs to be tested separately, or is this a composition? Then I don't need to test this separately. So then the rover and this navigational component form a unit, and I just test against the public interface of this rover. So those are the questions you actually you actually ask a little bit before, and in some cases this outside-in approach is better suited to carve out the design of what you want to do. So okay, but let's get started. We need a new test, and we're using 5am as unit test package. Rover, and I have Yas snippet, my own Yas snippet templates here. To create a 5am test package. So let me make this window here a little bit bigger. So this is the test package, and we use a package here which is something without this test. This doesn't exist yet, and when we compile this code, or let me first save it, cl Mars Rover. So I have created a folder for this already, rover test.lisp. So when we run this, we of course get an error that the 5am package is not known. So this is also the cool thing about Common Lisp. You don't need a fancy project setup where you define your dependencies in the project. You just fire up your REPL, use quick load or quick Lisp to load libraries, load packages, and then you can just use them, right? Good. So the other package that I know we'll be using is cl-gserver. So this is the package. This is the library I've created some time ago, and yeah, we'll be using this. So I just want to load it right away. And also what we can do, we can also use this as a dependency here, or as as a dependency for this package, cl-gserver and cl-gserver actor. So this is a sub package, because an actor is basically just a subclass of this gen server, of this g-server, right? So what now? So now it's missing a cl-rover.rover, so it doesn't know this package. Yeah, that's all right. Let's create this package. Let's create a new buffer, rover.lisp. Increase the font size a little bit, and then use snippet to create a new package. Project name is cl rover. Module is rover. Dependencies cl-gserver. Yes, and cl-gserver.actor. Exactly. We don't need closer mob. And I comment out this exports right now because we have no exports at this moment. Rover.lisp. Good, so let's compile this file. It compiles. Oops, there's this is an old error. Okay, so let me remove this. And in this buffer, I want the slide compilation information. Yep. Can I make this closer, smaller? No, not really. Okay, anyway, let's run the test here again and see if it passes. Yeah, it passes now. So we can actually now remove this dummy stuff and create a real test. So what do we test first? A trivial thing. I want to create a rover. So creating a rover, for creating a rover, a number of things actually have to work. So for example, we need to be able to make an instance. I forgot to run my Pomodoro. Yeah, let's run it. So we need to be able to make an instance of a rover. Yeah. And so we need to be able to create an instance of a rover, which we are not at the moment. So the error we get is class not found error rover. So let's create a rover class. Rover. So this should be a subclass of an actor, and we don't have additional slots, so the slot list is empty here. Let's compile this. Yep, and what we want to export now is the rover. And I think now, yeah, now we get a name conflict again, because I have defined this rover name here, and it was interned to the Common Lisp runtime system. But now I define it here as an export, so there's a name clash, and I can now decide. So Common Lisp gives me some options what I can do, and I want to take the new one here. And then when I compile this again, it should be okay. So when I run the test now, it passes. Create rover, test passes. Good. So now it gets a little bit more tricky, because what we want to do now is we want to test the initial state of the actor. Okay, and so this involves now a little bit more test setup, because we want to bring in this reporting facility right now, or already, right? So that we can create an actor using this reporting facility. So let's see how that goes. test initialize rover tests to initialize rover and state. So so what we probably need to have is so let's carve out this first in the REPL. So and then we can copy it over to reported state. Let's create a variable reported state, which we have nil first, and then we create a reporter, which is basically make actor a simple actor. So you can also define a simple actor which doesn't need this class definition. So it's basically a class of a simple actor that you need to give a name, and it can have a state. And I wanted to have the state right now. The state I wanted to have is the reported state. Yes. Is that all? No. So, and it must have a receive function definition, which usually is a lambda. With this lambda gets the parameters self, like the instance of the actor, then there's a message, and there's a state. So whenever a message is sent to the rover, this receive function is called with those parameters. And what I want this receive function to actually do only, so the only thing this receive function actually should do is it should set wait a second. So this message that this reporter will get is a state representation of the rover. So this message contains a state representation of the rover. So what I want to do is I want to set the reported state with this message. And then the interface definition of this receive function is that I must return a cons of two things. The first thing is return to the caller if the actor is called using an ask, and this is used to update the state of the actor. So I think so what we can actually do here is just use this. So should this be an ask, then the message, the new state basically is returned, and message will be the new state of this actor. Okay. So wait a second. Okay. Good. So there are two style warnings. State is unused and self is unused. So we could do a declare unused blah 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 to actually get rid of those warnings, but that's okay. That's fine for now. So we have a reporter and we have a reported state. What we can do now is send something to this rover, like, I don't know, a list with foo send. Wait a second, I need to name the reporter first. Send foo reporter. Okay. So this info message is coming from the cl-gserver library. It's a log4cl message, where it just said where it just outputs a handler result. But we can actually check now the reported state, and it is foo. Okay, so it works. Okay, so this is cool. So we can actually now put this here, and use this here. The only thing is that we don't use def parameters, but we use the let. Although we might need to see if when we add more tests and we have this setup continue repeatedly, that we refactor this a little bit into some more global thing. Let's see. So okay, so we have the reported state, which is initially null. Then we have the reporter, which is a, can I just copy this here? Which is just this, make actor. I don't need this act because I have imported this stuff. So the state is not a global variable, but it is this. And so this should go to the end of this line. So we are now in this let. So whenever the reporter is called, we need to define actually now how will the reporter how will the rover report its state or an obstacle to this reporter. Then we need to so yeah, this is something we need to define, but we need another thing now here. So we need, of course, the rover, right? So make instance rover, and we need to give it this reporter. Reporter. So of course it must know about the reporter because it must report its stuff to it, right? So not now. So let me see how far we get. I think let me set up a test here. Wait a second. I think I need to set up a sleep here because this is all asynchronous setup and I need the rover to wait a little bit. We can later maybe refactor this to some wait function which probes, so we can specify a larger timeout, because specifying such a small timeout can be really troublesome if you have this if you run this test on a slower systems or so, and actually it's not dynamic, right? So but let me also define what we expect from, so we will probe this reported state, right? So we will probe this reported state, and I want to now define how this reported state actually should look like. So let's back up for a moment. I think we need to differentiate between the internal rover state and what it reports to this reporter. So there might be a structure of in the rover that contains the state of the rover, but what it reports to this reporter is certainly something else. So it might be something detached from the actual rover state and different representation of its state. So what we could do is that it could be something like, if we go back to the to the REPL. It could be an associative list, for example, that it reports its data, its state as a associative list. So it would look like list, and then you have conses. Like if I want to have a position in this, I have a keyword position, and then I would have a cons of 1 for the position, and I could also have a cons for the direction, which initially should be north. Okay. All right. So let me write this to in parameter a list. And now I can ask the a list using assoc. The item should be this position, and I need to give it the a list. And then I should get this position cons. And when I just want the second part of this cons, I need to get it with cutter. Then I just get the position. And similarly with the direction. So so what we can actually do is so this reported state is actually then such an associative list. Then we can set up some then we can set up some helper functions, assoc, position, a list, and when I just want the second part, I can also do the cutter here, which will give me the second part. And the same for defun get direction a list. I also want the cutter of the assoc direction. Yeah. Let's give this a try, because this will help us in the is statement. So we can, for example, now here check for equality of a cons 1, 1, which should be the initial position, and we can say get position and give it get position from the reported state. Right? And this would be our first this would be our first test, our first assert. Initialize, is it not here? Initialize rover. I think I haven't interned it yet, because the syntax completion will only work if I have interned it. So I need to control CC to actually intern it. So, and then we have some what is it here? Unused variables, but compilation successful. So there are only unused variables. This is fine. So maybe we can get rid of those for style warnings. Undefined variable reporter. Yeah, it's indeed undefined. Oh yes, it is indeed undefined because I need to use a let asterisk. A let asterisk makes the initialization of those variables serially. So so I need to have this reporter set up so that I can use it here, and then I need to use this let asterisk. So let's compile this again and see what we get. And this looks better now. Yeah, okay. And now we have, of course, so we're trying to make an instance of this rover with a reporter, but this rover actually has no, so it has no slot to accept this rover or to get initialized in this way. So what we need to do is to set up to define this to define slots for this rover, namely the reporter. And I just want to so so we can define new slots just like this, right? So just add a new something like this, and then you will have a slot in this class. A slot is something like an instance variable, so we will have the slot. So when it should be initialized from the outside, you need to have this init arg, and this init arg actually need to have this reporter name, so that I can call it with this keyword reporter. So, and if I don't specify it, then it should be initialized with nil. So nil gives me yeah, is a default value, right? Okay, so let's have a look. Let's redefine the rover, and let's run this again. Let's see what we're getting. Okay, so it could create the rover now, and it says now that get position reported state is nil, but it should be 1,1. Yes. So now we need to have some rover state set up. And therefore I want to define a struct which is called rover state. And this rover state should have this rover state should have an x position, which is initialized with 1. It should have a type, and it should be of type of integer. And it should have a y position, initialized with 1, type integer. So this is actually, even though Common Lisp is dynamically typed, it does some type checks. So you couldn't put in a string to this position slot. Then the compiler would fail. So the compilation would fail. So there are some parts of static type checking in Common Lisp. Or maybe it's implementation dependent. I don't know if all implementations of Common Lisp do this. So this we are using SBCL here, and it does it. So let's compile the def struct, and so I think this will still fail because there is still a lot of stuff missing here. So now the rover should report its initial state. So we need to create we need to implement initialize instance. So we need to create initialize instance, and at the after keyword so that this initialize instance is called after the rover was initialized, and and in case it has no state, I want to create the state internally. So we can say with slots. This is how you access the slots actually. So we can say with slots reporter and cl-gserver state. This is the state of the parent class, and the slots should be held on the, should be retrieved from the self, from the rover. Then when the cl-gserver state is null, then I want to make a new state. Then I want to setf gstate make rover state. So I want to make a new, I want to set a new state when the state is null. Right? And then I want to send this state in this associative list form to the reporter. So when we have a reporter, then create reporting state. Create reporting state. Okay, this was one Pomodoro. I actually don't want to go, I don't want to, so we do a full one again, but that should be it then. I hope we get it working so far, that we have carved out the concepts of how this should be continued. So create a reporting state from the cl-gserver state. So the state we have just set, and this should be a G. And I don't like that I have to write this in full all the time, so we can make this a let and call it just state. cl-gserver state. This is the let. So wait a moment. Let state I'm not sure this works with slots like this. I'm not entirely certain. So I would actually first need to get it running, and then we can make this refactoring. So okay, so when the state is null, then set a new state. When there's a reporter, I want that you send the reporter this state representation. Yes, I want to send the reporter this state representation. And and this ASOC list should look the same as we have just carved it out. So create reporting state, and we have a list of cons with position and a cons of. So when we have a def struct, we can access the slots of the structure like this rover state exposition. This is, since this is a macro, those things are actually created from the macro, and I can just use them. State cons rover state y position. Rover state y position. This was the first cons, the first association, and then we have a cons with direction, and the direction is rover state direction. Yeah. Okay, so it compiles. Let's see how far we get our test working. And it passes. Wow, this is cool. This is fucking cool. All right. So we can also test now for the direction. The direction is just a symbol, so I can use eq. And I want to have the right direction as north. Then we can say get direction of in the reported state. And let me add something wrong here, because I want to see the test actually passing. So, but I want to have it red before I want to have it green. So it fails now, but let me add north now. So the state is actually north. Yes, okay, and it passes now. Good. So this is for the initial rover state. And as you can see, we have quite a bit of test setup here. And I'm wondering if we can reduce that. I don't know. And what I also want to do is get rid of the sleep. But I have prepared something. Let me just copy it over, because this took me too long to develop. Actually, I'm not yet complete Common Lisp expert here. So this is a function assert state, which takes a function and it takes a maximum timeout. So this can be quite large actually. So but it probes. So it calls this function in every 50 milliseconds, and as soon as this function returns true, this assert state will return true. And if not, it will probe until this maximum timeout, this max timeout has timed out. So what we can do now, we can get rid of the sleep and just say, how do we use that? Yeah, so we can just say is equal t, and then we use the assert state, and here we have yeah. So here we have the lambda. I need to look it up. So the lambda has no parameters, and yeah. So what we check in this lambda here actually is this, right? So this is what we check in this function. We probe that this cons is equal the position of the reported state. So the reported state is probed repeatedly until either we get a timeout, or, and I need to put in some, this can be probed for 3 seconds. Right. Let's see if this works. Undefined function. Yes. Good. Let's run this test. And it still passes. Yep. So let's do the same thing for this. And I'm wondering whether we can actually put this into, so that we have only one test. No, because I want to know exactly which test actually failed. So lambda, and then I want to have this in here. Is let test. Let's see. Okay, there's something. Ah, yeah, okay, so we're missing this parameter 3, where we define the maximum timeout. We could actually make this optional a default value. I just don't know exactly how default values are defined. I need to look this up, but I want to get this finished also. So let's continue. So let's get started with actually sending the rover commands. So move forward. Move forward. Yes. Test for moving forward. So now we need to have again our test set up, and I want to copy it for now. So we need to later think about how this can be, how we can refactor this to remove the duplication, but for now this is okay. So I want to first make it run, and then we can remove the duplication. So right, so here we need to send something to the rover. Send the rover and we actually can send it the command as a list of characters. So this is the interface we should implement, right? And then I want to assert that when I move the rover forward, that the position it reports to the reporter has an increased Y position, right? So this is what we need to do. We need to move forward. We actually also need to take the direction into account, but for simplicity reasons, I don't want to do this actually now. Unmatched brackets. Okay. So we need to actually also run this test. Move forward. So now we have a failing test. So this lambda assert state cons 1, 2 fails. It evaluated to nil. Well, that is clear because the rover actually doesn't process any commands. So we need to implement the receive function, receive method of the rover. So we have again the type. This defines the type and the instance of the type, and then we have this is how this message is how this receive function is defined. We have the message that was sent to the rover, and we have the current state. And the current state is whatever the current state is, right? So whatever we have defined here in initialize instance, or if we put it in from the outside, right? This rover, this is the state of the rover as we use it here. So when we receive, so what we receive in this message is actually this list of characters. And so we must now process this list of characters. So what we could do, we have a state which should change all the time, and we have a list of characters. So what we could do here is actually use a reduce function with a lambda that takes the rover state and the command. Yes, and what I put in is the message, because the message is the list of commands, and I want to have the initial state of this no, it's called initial value, I think, isn't it? Yeah, the initial value of this reduce is the current state. Or actually, not actually the current state. I want it to be a copy. I want it to be a copy of the current state. Because if we don't do a copy here, if we don't copy the structure, the state is actually updated before the state of the rover, of the whole rover, is actually updated before we can respond with our cons. So the interface of this receive function is that you have to return a cons of something that is returned to the caller, the same thing we have here on the left side, and the new state it should take. But if we use this current state here in the reduce, we might change, because because not everything in Common Lisp is functional and immutable. So this current state is actually not immutable. So we have to take care ourselves that we copy the structure before we put it into this reduce. So, but I think this should not be in here like that. We should just have a let new state, and then we have a command processing unit, maybe, which is a collaborator, but it's composed because this might not make sense for anything else than a rover. And this processes commands. Process commands. And it takes the message and the current state, or actually a copy of the current state, define what a process commands, the commands and the rover state. And then we don't need to copy the structure here again. Just can take the rover state and use the commands here. Yes. So let me evaluate this. Okay, what does it say? Style warning, unused. That is true. That is true. So this process command still doesn't process anything, right? So I just need to get this structure here in place. So we have a new state here. So after the commands were processed, we have a new state. And I need to communicate this new state now to the reporter. When reporter send reporter create reporting state with from the new state. And actually I want to carve this out. Report state, new state. Report state, self, new state. Diff on report state. So this is, I just want to rover. This is the rover, and this is the state. When rover, when reporter. So we actually need first the slot with slots reporter. Rover. Yeah. What is this? Undefined variable, new state, right. It's only state. Okay, this is okay. This still has this problem. And what we also need to do is not only report the new state, we also need to respond with new state to a caller and return the new state from this receive function, so that a new receive function will, so that it internally can update its state. So this is what this actually does, right? Okay. So I could also remove this one, refactor this one with report state, and it should take self and cl-gserver state. Okay, let's see. It compiles. Rover state is defined but never used, so this is from here. Yeah, that's okay. That's okay. Let's run the test. And they certainly also still, so they certainly still fail. But let me check if the other tests still pass. So this passes still, and this passes also. Okay. So of course the rover doesn't process any commands yet, right? So what we do is, yeah, we have to process the commands in here. So in this so in this lambda, we need to cont over over the command, right? And if the command is AF, I want to move forward, and I need to give this move forward this current state. Yeah. So this complains now that this function is not known. Move forward. Rover state. So what we can do here is just incf, because the state is an integer. We can incf rover state x y position, incf rover state y on the rover state. But then so this will increase, so this will change this state, and then we have to return this state, so that this whole so this process commands must return something, because this process commands is part of, well, it must return a new state, right? And so I just want to finish this up. I just want to get this test working, and then I want to maybe I continue some other time with this, but I think we have carved out enough that that you see how this works. So so this process commands must return something. No, this move forward must return the state because it's part of the reduce. So the reduce takes the new rover state of each iteration, if you want, as a new state to this lambda. Okay, so we must return something, and also and this reduce returns a new state also. So let's see if this gets it working. Yes, and it does. So cool. Right. So we can actually move. So I'm running out of time. So what we certainly must do is to refactor this setup here in the test. So this is what I would do now. Basically, I would do the refactor this whole test setup. But I think this should be doable quite easily, so that we just have maybe one variable here in this let, and the rest is set up someplace else, and because it's always the same, right? But otherwise, of course, we can implement more of the rover and see. But this is something this is something you can do. I've done this often enough. So yeah, that's it. So we've seen a test-driven development. We've seen actor pattern. We've seen how something can be designed, or different designs for the Mars rover, and different thinking processes that could be involved with this. And we've seen a little bit of common Lisp, how this works. So thank you for watching. See you next time.